Assalamualaikum and welcome back. Let's continue with solving a few examples. So let's start with example 7. So here we are asked to use spherical coordinates to find volume of the solid bounded above by the sphere and below by the cone. Okay, alright, so I need more room than this. Okay, so here we have a solid bounded above by the sphere. So x squared plus y squared plus z squared is a sphere of radius 4, and the center of the sphere is at 0, 0, 0, or the origin. And here we can write this down as, remember, x squared plus y squared is x squared plus y squared plus z squared is rho squared, the relationship between x, y, z with rho, phi, and theta. So this is equal to rho squared equals 16, or another name for that circle, that sphere is rho equals 4. Okay, let's sketch the sphere. So here we have a sphere of radius 4. So let's say that's 1, 2, 3, 4. See, that's a 4, that's a 4. So we have a sphere of radius 4. Let's say that's a 4. 1, 2, 3, that's a 4. Here we have negative 4, 4, 4, negative 4. So here we have a sphere of radius 4. X squared plus y squared equals 16, or another name for this is rho equals 4. Okay, and then we have a cone, z equals square root of x squared plus y squared. So if you recall from mathematical methods 1, this is a cone that is right in the middle of the octant. Okay, so remember we have z is this, and the process of sketching this, if you recall, let's say we well, first of all, from here we know that z is larger than or equal to 0 because of the positive root there. Okay, squaring both sides, we have this. Okay, now the view from this is just a revision really. The view, so to sketch this we need a view from the front, the back, the front, the side, and the above view. Okay, so for the view from above, we let z as a constant. So let's say we let z equals 4. Then we have 16 equals x squared plus y squared, which is really a circle of radius 4. Okay, so this is a view from above when z is excuse me, when z is 4. Okay, and let's say we need a view from the front. The view from the front is when we let x as a constant. So let's say we let x as 0. So we have this x, we have z squared is, remember we want to sketch this, we have z squared is equal to y squared, and if we rewrite this we get z minus y, z plus y equals 0. So we have two straight line. One is z equals y and one is z equals negative y. So if we plot this on the yz plane, you would get this, z equals y, and here we have z equals negative y. As you can see, this is right in the middle of the quadrant, so it's 45 degrees. So this angle is 45 degrees, or pi over 4. And this angle is pi over 4 because it's right in the middle. But of course, because we want z to be larger than 0, we don't consider the one below the y-axis, because that is when z is negative. Okay, all right, and then we need the view from the side. So for the view from the side, we let y as a constant. So let's say we let y equals 0. Then we have the equation would be z squared equals x squared. So using the similar process as before, we end up with equation of two straight lines. One is z equals x and the other is z equals negative x. So if we plot this on the xz plane, same thing for z equals x, we have a straight line right in the middle, and for z equals negative x we have a straight line as well. And here same thing, this is 45 degrees or pi over 4, and this angle here is pi over 4. And since we only want z to be larger than or equal to 0, we don't consider the one below the x-axis. Okay, so from these three views, the view from above, the view from the front, and the view from the side, we get a cone. Okay, let me sketch the cone. Well, in here, so sketching the cone. Okay, let's say here we have a cone, like so. You can draw it larger than that if you like, but since we have it says the solid G is hang on, solid G is bounded above by the sphere and below by the cone. So our solid is, say, it's below the sphere, and it is bounded above by the sphere and below by the cone. So our solid is, well, this is the shape of our solid, which is really a shape that looks like an ice cream. Okay, so this cone is governed by this equation, x squared plus y squared. And remember here the angle is right in the middle, 45 degrees. So another name for this cone is phi equals pi over 4. Okay, so I hope you remember that. Oops. I hope you remember from now on, if you have z equals square root of x squared plus y squared, that is a cone. And another name for that cone is phi equals pi over 4. I know some of you can sketch this very quickly, but I just want to refresh your memory on some methods of sketching the surfaces from Mathematical Methods 1, just in case you forgot about it. Okay, now I want to erase this. Okay, so now we want to find the volume of the solid. So remember, volume is dv integrate over solid G. But since our solid is part of a cone and part of a sphere, we're going to use spherical coordinates. Okay, we're going to use spherical coordinates. Let's see. Okay, all right, here we go. So volume, similar to Cartesian and cylindrical coordinate, volume is still dv over solid G. So this is our solid G. And we're using spherical, and for spherical, dv is equal to this whole thing, rho squared sine phi d rho d phi d theta. Okay, so for spherical, dv is rho squared sine phi d rho d phi d theta over solid G. Okay, now we are in the process of finding the limits for, so we need the limits for rho, limits for phi, and limits for theta. Okay, you just refer to your solid G. Okay, let's find the limits for rho first. Okay, remember how you measure rho. Rho is measured from the origin. Okay, so you start from the origin, and then you just draw a straight line across your solid. Okay, and as you can see, it does start at the origin, and then it stops, well, whatever straight line you do across your solid G, it does stop on the red sphere. Okay, so the limits for rho is going to be from the origin, and then it stops on the red sphere, which is governed by the equation rho equals 4. So the limits for rho would be from 0 to 4. Okay, now let's get the limits for phi. Okay, for phi, remember phi, we measure phi from the positive z-axis. Okay, you measure phi from the positive z-axis. Right, let me make this larger. Change the color to blue. Okay, so from the positive z-axis, you draw an angle across your region. Well, it starts here and then it stops on the purple cone. You can do it this way as well to measure this. Okay, so whatever it is, it does stop on the cone. You can do it forward and backward, same thing. So it does start on the positive z-axis where phi is 0, and then it stops on the purple cone which is governed by this equation and also this equation. So phi is going to be from 0 to pi over 4. Okay, and now the last step is to find the limits for theta. Okay, how you measure theta? Theta is measured from the positive x-axis, anti-clockwise direction. So to do that, maybe if you're not an expert yet, you just project this solid onto an xy plane. Okay, then you can see that the projection of the solid would be a circle. Okay, one whole circle. All right, so for that, theta is going to be from 0, so it's a one whole circle, so 0 to the whole rotation there, so 0 to 2 pi. Okay, all right, so that's how you get the limits for rho, phi, and theta. Okay, so now let's evaluate this. Okay, same thing, we evaluate the inner integral first. Okay, so which means that we integrate with respect to rho. So here we consider sine phi here as constant, differentiate rho squared, we get rho cubed over 3. Replacing rho with upper and lower limits, then we get the limits for rho are 0 to 4. Okay, what is 4 cubed? 4 cubed is 64 divided by 3. Okay, 64 over 3. That would be after integrating rho. Okay, so we get 64 over 3. I'm going to put it here. And then we still have sine phi, d phi, d theta. Phi is from 0 to pi over 4. And theta is from 0 to 2 pi. Okay, the next is integration with respect to phi. Okay, so here we have 64 over 3, 0 to 2 pi. Integrate sine, we get negative cos phi. Okay, and then replace phi with upper and lower limits, pi over 4 here, and we still have theta. Okay, if you recall from high school, we have this triangle where we have this is 1, this is 1, this is graph 2, this is 45 degrees, this is 45 degrees, well, pi over 4 is 45 degrees. This one is in radian, this is in degree. So from here we can see that cos pi over 4 is adjacent of a hypotenuse, which is 1 over square root of 2, or you can use decimal value if you like. Okay, so here we have 64 over 3. So here we have 0 to 2 pi. We have negative cos pi over 4, upper limit, minus the lower limit, negative cos 0. And we still have d theta there. Okay, and oops. Okay, let's continue here. We have 64 over 3, 0 to 2 pi. Well, cos pi over 4 is 1 over square root of 2. So here we have negative 1 over square root of 2. And cos 0 is 1, so we have plus 1. And we have d theta. So this is a constant, right? So we can put it here. This is 2 pi. Right, so we have 64 over 3, and here we have, you can write this down as square root of 2 minus 1 over square root of 2. That's a constant, and then we have d theta, 0 to 2 pi. Okay, integrate d theta, we get theta, so here we have 64 over 3, square root of 2 minus 1 over square root of 2, and here we have theta from 0 to 2 pi. So simplify that, we get 128 square root of 2 minus 1 pi over 3 square root of 2. Okay, or you can leave your answer in decimal number. Okay, all right, so that is how you find volume using spherical. Usually we use spherical if our solid is part of a sphere and a cone. Okay, but remember, dv is rho squared sine phi d rho d phi d theta. Okay, thank you.